shared, at least it should be to everybody. I'll double check this one more time. I mean that. Anyway, I can tell if this is actually the screen that's being shared. All right, yes, share. All right, we should be good. Should be all good. Yes, you are. So here you go.
Yeah.
Here you are.
Okay. All right. Sick. We're gonna start with some vector. Ooh, actually, let me get the lights. Do this one. Yes. Okay. We're gonna start with some vector review. How do you guys feel about vector stuff in general? We know how to find a magnitude, know how to find a unit vector. Chillin'. Sweet. Yep. Okay. Awesome. How about dot products? How do we feel? Pretty good. Yep. You're just returning it. And kind of a conceptual way that I think gets skipped over sometimes of thinking of dot product is it's measuring how in line the two vectors are. Because if they're perfectly in line, then it'll be equal to the magnitude of the first one times the magnitude of the second one. And if they're perfectly perpendicular, then the dot product is 0, right? So the dot product increases the more in line they are, and obviously with also the higher magnitude, right? Yeah, that's an example. I feel like you guys got it. Chilling. You do it with the angle between. Awesome. How about cross product? How are we feeling about cross product? Okay. Yeah. It's kind of it's the cross product in the same way that the dot product kind of measures how in line two vectors are. The cross product kind of measures how perpendicular they are. So if you notice, as far as just finding the magnitude of the cross product, it'll be equal to AB times sine theta. So if theta is 90 degrees, then it'll be the magnitude of A times the magnitude of B. This comes into play when we're thinking about the cross product more in terms of torque, less so in this class. But when we're talking about it as far as calculating it with our vector output, because that's our other big difference between the dot product and the cross product, right? Is the dot product will give us a scalar value. The cross product will give you a vector, and that vector will be orthogonal to both vectors you crossed. Gives you the normal vector. Exactly. Do you guys want to go through calculating one, or should we skip? I'm good either way. Okay, awesome. Awesome, awesome. Okay, I'm trying to remember if I have, here's my example. Okay, so if we want to cross the two vectors, oops, is it gonna let me? Haha, 2, 3, 4, and 0, 2, 1. You might see this notation with IJKs. It's also pretty common to see it as with like brackets. I like that better because it's shorter, but physicists like this more. I don't know. Then what we set it up as is we have our i's, which are going to be kind of like our x's, j's, and k's, and then line up our x's for each vector, y's of each vector, z's of each vector, right? And we set this up into a matrix. And then we take the determinant of this matrix. If you aren't familiar with the determinant and how that would usually be calculated, that's fine. Because in a 3x3 case, there's just kind of a formula to it that we can show you. I'll just write it out here and we'll do it together. So the first thing you're going to want to do, I call it the cover up method. That's how it was taught to me, is, so this is kind of the notation for the determinant, is the two lines. It's going to be equal to I hat, which just means this is the x component of our vector. And then I'm going to cover up these two, the row and column that have I in it. And then I'm going to multiply this 3 times 1 is 3, and then subtract what I get multiplying that way. So 3 times 1 is 3, and then minus 2 times 4, which is 8. Now, yeah. Oh, okay, sorry. I thought you were getting my attention. Then for J, this is a tricky one that people forget sometimes. With J, we have to subtract it instead of add it. It comes from a whole bunch of crazy properties that we can get into later if you want. And then I'm going to multiply these two and subtract by the multiple of those two. So I get 2 times 1 is 2, minus 0 times 4 is just 0. And then finally, I'll do my k vector. This is once again added. I cross out those two, and I get 2 times 2 is 4, minus 3 times 0 is just 0. And so when I do simplification, and if I want to write it in terms of like brackets in a form we're more familiar with, then I'm going to get -5, -2, +4, like that. So that's going to be my cross product vector. It's going to be normal to those two vectors. And its magnitude will be equal to the magnitude of A times the magnitude of B times the sine of the angle between them. So that can be useful for if we want to find the angle between two vectors that are in like three-dimensional space sometimes too. But you don't really use it much in Calc 3 in that way, but just so you know. Are you good? Awesome. This is just going through what we already did. Partial derivatives, Howard's turn.
Yay. Alrighty, partial derivatives. Let's do it. So I'm assuming you guys know what partial derivatives are, but we'll go over them just real quickly. We don't have to do an example or anything, just because I bet you guys are good with it. But so partial derivatives tell us how a function changes with respect to one variable while keeping the other variables constant. So that's pretty much what all they are. I'm assuming you guys don't really care to do a practice problem with them. And yeah, I figured. Do you guys know about that little factoid in the bottom? Cool. Sounds good. All right, so tangent planes and approximations. Do you guys want to go over this? Yes. All right, cool. Sounds good. So a tangent plane approximation is basically using the Taylor series as our approximation. That's basically what it is, right? So if I were to look at this, right, this is our definition. So if we're given a function with two initial points, we can then use that function and the two initial points to use a Taylor series approximation in 3 dimensions to find what our tangent plane would be using those 3 parts of it. So we will go ahead and do an example with that as well, where we find our Taylor series approximation. I'll wait until you guys are done writing before moving on. And if you guys want, right, so our one-dimensional Taylor series, right, or our two-dimensional Taylor series rather, would normally be something like this, where we have like an f of x is equal to f of, let's call it x naught, at whatever point we were given. Then it would be plus f prime of x naught times x minus x naught. And that would be our first order Taylor series approximation for 2 dimensions. So our 3-dimensional Taylor series approximation will give us our tangent plane in 3 dimensions, which will look exactly how we have it right up here. Let me know whenever you guys are ready.
Yeah, I got it.
You got it? Cool. So let's do an example. So let's find the tangent plane given with this equation and that initial point. Do you guys want to try this by yourself real quick, or do you guys want me to walk through it? Try by yourselves real quick. I'll give you guys a couple minutes to do that, and then we'll continue after you give that a shot. Nice and spoopy. All right, natural logs aren't too much something to be afraid of. Oh. Antiderivatives of them?
No, I said.
Oh yeah. So chill. Extremely chill. Correct.
To clarify, x naught, y naught is the center of your approximation, and then x and y is outside of that.
So we take the partial first and then plug in?
Yes.
Okay.
Yeah, so you need to evaluate your partials each time. Yeah. It's kind of cool. I'll probably give you guys like 1 more minute-ish. Yes. You guys will fail the class. We will make it our personal agenda to fail you if you don't complete it within 1 minute. For professional reasons, I am joking. Calc 2's tonight, right? Our other review. Done. All right, cool. So, what'd you guys get?
We had 10x minus 10 plus 2y.
I got 5 plus 10, x minus 1 plus 2, minus 1.
Yes, so that is, yours was correct. And then you got what?
Oh.
Yeah.
Because you just plug it into your.
Yeah. So, right, we start out by taking our partials, right, in respect to each one. And then we evaluate the partials at those points. So our partial in respect to x should be evaluated at about 10.
Yep.
Right? And you guys both get that?
Yep.
Cool. So we take our partial in respect to y, and that should be evaluated at about 2. And then just our initial function we evaluate, and that equals 5. So you just put it all together, and that's where you get your final answer. Yeah, you cannot forget this part. Because basically, like this part, the part with the partials, gives you how, like basically gives you the plane that is tangent to the surface. But this point moves the plane to where that point is tangent. Yeah. So you cannot forget that, yeah, that right there. So yeah, that's with that slide. Now we can go over the gradients. Now it's back to Izzy. Yay.
Okay. So we're gonna go over the gradient of our vectors. How do you guys feel about this concept overall? Okay, yeah. So the gradient, it's a vector that describes how our surface is changing. It is a vector with the partial with respect to x and then the partial with respect to y. Our gradient, yeah, it describes how our surface is changing. It's kind of the two-dimensional version of our derivative in some ways, but things get wonky the more dimensions we add, right? The gradient also points in the steepest direction along a surface. So what I have a picture of here, and then I think I added, yeah. So this is a screenshot from All Trails, LOL. And these are contour lines. Along our contour lines, our gradient or our slope is 0 if we follow a line going across. Our gradient will point perpendicular to our contour lines like that, no matter where we put them. And it'll always be our steepest slope will be at the gradient, right? Awesome. And that's kind of what this is showing as well. So for the next few concepts, I just have like one surface that we're going to be working as our example and finding each thing as we go. So you might want to write down this surface if you guys want to do an example. But let's find the gradient of this surface right here. So our gradient is going to be equal to our partial with respect to x and then our partial with respect to y, which in this case, do you guys want to shout out the partial with respect to x? 3x cubed plus 15y. And then our partial with respect to y.
36
Mm-hmm.
y plus 15x.
36y squared, right? Yep, totally. So that is our gradient. So for any given point x and y, we can plug them in, and the vector that it spits out will be in the direction of steepest slope on the surface. That makes sense. Cool. And that's what I've already showed you. So now the directional derivative, kind of building off of the gradient, the directional derivative describes how much a surface is changing in a particular direction. In other words, how steep is the surface along a particular path. So if we think back to this example, our gradient showed the steepest slope at any given point. Our directional derivative says, okay, if I'm following this path, how steep is it going to be? And remember when I said that our dot product shows how in line two vectors are? That relates to this, where if we define a unit vector that has the direction of our path, then we dot it with our gradient to see how in line it is with that gradient to see how steep it is, if that makes sense. This unit vector can, it can be just any vector with a magnitude of 1, and that can include cosine theta, sine theta, right? Where theta is, some angle based off of polar coordinates. And we can use that to find our steepness or our gradient, or not gradient, or steepness. Okay, so using the surface from before, find the derivative in the direction of this vector, 3, 4. So what is our first step going to be? Finding the unit vector, exactly. So the magnitude of our vector, 3, 4, is going to be equal to the square root of 3 squared plus 4 squared, which is 9 plus 16, 25. Yeah, so our magnitude is 5. Beautiful. I love when it's an actual number. So that means our unit vector, I'm going to write it like that, is equal to the x component divided by the magnitude and the y component divided by the magnitude. So 3/5 and 4/5. Now, to find my directional derivative, I'm going to dot it with my gradient, which, if you'll remember, is, yep, so 3x cubed plus 15y, comma 36y squared plus 15x, dotted with 3/5 and 4/5. And it just will scale those two, according to that. We can write out the whole thing if you want, but long story short, that's what's going to happen. Does that all make sense? Okay, awesome. Sweet. Whoops. Okay, now let's talk about finding our critical points. So in the same way that when we were dealing with 2 dimensions and we were finding our maximums and minimums in like calculus 1, we took the derivative, set it equal to 0, and where it equals 0, we knew we had either like a maximum there or a minimum there, right? Now that we're in, or actually I'll get to that in a second, but we're doing basically the same thing now that we're in 3 dimensions. We just have to know that both the partial with respect to x and the partial with respect to y are equal to 0 instead of just one of them, right? There is an or case where neither of them, where one of them doesn't exist, but those are kind of like special cases. Those are more discontinuities than they are maximum or minimums that we're trying to find, right? So let's find the critical points of our surface. So we already found our partial, our partial with respect to x, which we found when we took the gradient, is 3x cubed plus 15y. And I'm going to set that equal to 0 so I can find that point. And then our partial with respect to y that we found was 36y squared plus 15x. I'm also going to set that equal to 0. Do you guys want me to go through the algebra of this system of equations, or do you want me to cut to it? I can do either. I'm just wondering if you guys want practice at that point, at that part.
Okay, but you solve for one in terms of the other variable.
Yes, exactly. And I mean, I can show you like just the first step, y equals, I rearrange this equation to get y equals negative x to the third over 5, plug that in there, solve for x, solve for y. So that's the nuts and bolts of that. And then spoiler alert, because we have x's and y's to higher powers, you're going to get 2 possible answers, okay? So your 2 possible answers are going to be 0, 0, and a number that's pretty nasty. And I apologize for that. I didn't realize my numbers were going to be nasty until I got to this part. But it's going to be about negative 1.598 and 0.816. In reality, there's some square roots in there, and it's pretty gross, but we can approximate. That's what we're here to do as engineers. And so these are our critical points. They are where, hey, oh my gosh, I'm so good. This is crazy. Sorry, we know each other. That's wild. But this is where both of our derivatives are equal to 0. And we do have to check and make sure that, like at 0, 0, 0.816 is not a valid critical point. They have to be in their pairs, if that makes sense. Yeah? Sweet. So now, once we have our critical points, we want to figure out whether they're a maximum, a minimum, or a saddle, right? We want to figure out, like, is this a maximum or is it a minimum? Because those are 2 very different things when we're talking about what we want out of our functions. The way to do that is something called the second derivative test. It says that if we have our second derivative in terms of x times our second derivative in terms of y minus our mixed derivative squared, or our first derivative of x, and then you derive it in terms of y, all of that together is equal to d. And then we have different rules for what it means for if it's a valley, a saddle, or a hill. And we're evaluating it at our critical point. This is similar to in like calculus 1, when a way you could figure out if something was a maximum was that you would take the second derivative and then see if it was concave up or concave down. We're doing a very similar thing. We're just now in 3 dimensions. So do you guys have any questions about that? I went kind of fast. Did you guys talk about this in terms of a determinant of a matrix, or was it just these formulas?
That just kind of ended up being
What this ends up being? Okay, yeah. Yes, this comes from a determinant of a matrix we use in our Taylor series, but also you can know the rules, and either way will work. So either way is good. But yeah, let's find out if the critical points that we calculated are going to be maximums, minimums, or saddles. Okay. So the first thing I'm going to do is I'm going to take my second derivatives and get my formulas for all of those, right? So my f(x), or my second derivative in terms of x, is going to be equal to, sorry, and as a reminder, our gradient, just so we can keep track, our gradient is going to be 3x cubed plus 15y, and then 36y squared plus 15x. Cool. So our second derivative in terms of x is going to be 9x squared, right? And then our second derivative in terms of y is going to be 72y. Yep. And then, sorry, making sure I did it right. Yep, just 15. Perfect. So now I can plug in my critical points to get a value for each of these. So at 0, 0, plugged into each of these, I'm going to get 0 for my second derivative in terms of x. I'm going to get 0 for the y one as well. And then fxy is going to stay the same. It's 15. And then for our other critical point, which is nasty, 0.816, like that. We're going to get, did I calculate it? I probably did. It's, let's see here. I didn't calculate it fully. Long story short, it's a pretty big positive number, right? Because we're going to do a negative in the squared and then multiply by 9. Somewhat big positive number is how we're going to think about it for now. And then my second derivative in terms of y is going to be probably an even bigger number, also positive, right? When I plug in this y into there, it's going to be 72 times 0.81. And then my mix is going to stay 15. Perfect. So now I'm going to plug these into my d equations. So I'm going to move over here. D of 0, 0 is going to be this one times that one, which is 0, minus this one squared. So we get minus 15 squared, which is negative 225. So my d is negative, aka less than 0. So that means it's a saddle, right? So now we know 0, 0 is a saddle. And then my d of that stuff, I calculated as 1125, long story short, which means that d is greater than 0. So now I have to look and see if my my second derivative in terms of x is greater than 0. And we see that it is. It's positive. So then that means that it has to be this case, and it's a minimum. Does that all make sense? Awesome. Okay. We can go through and do all those steps with a different example if you guys want to. That's an option, but if you guys feel good, we can also move on. Do you want to do another example, move on, or do you want to hit any of these points specifically? No? You're good? Okay, sweet. Howard, I think it's you.
Yep. Thank you, madam. Yeah. Lagrange multipliers. We like the Lagrange multipliers. You don't? What's wrong with Lagrange multipliers?
6.
They are useful.
Yesterday.
See? Lagrange multipliers, man. All right. So Lagrange multipliers, what are they? Lagrange multipliers allow us to solve optimization problems. That's like the main function of Lagrange multipliers. So they are actually really useful. They can be really useful in a lot of applications. I personally have not used them yet because I'm a itty bitty sophomore, but Izzy has. So, there are applications out there. So we are going to do an example with Lagrange multipliers where we are going to do with golf balls. And if you guys look in OpenStax, this is actually in OpenStax and it goes into deep depth on this specific problem. If you guys want to look at it later. So this is going to be our example. So we have a golf ball manufacturer has developed a profit model that depends on the number of golf balls X sold per month and the number of hours per month of advertising Y. So that is the profit model. But there is a budgetary constraint function relating the cost of golf balls and advertising, and it is that function right there. So now we have to figure out what is the optimal profit for the budgetary constraint that we have. So that is where we are going to use Lagrange multipliers. That is our example right there. So we have our main function and we have our constraint. Our main function is our f right there, and our constraint is g. What is the first thing we think we want to do when doing Lagrange multipliers? Do you guys remember? Let's see if this will spoil it. So the first thing that we want to do with Lagrange multipliers is we want to set this equation to be true. This is basically what Lagrange multipliers are. That is the gradient of f is equal to lambda, some variable lambda times the gradient of g. That is our basic Lagrange multiplier equation right there. So if we were to start out by doing this, what is our gradient of f? They are indeed. Yep. So we'll break it into two parts. We'll break it into either I and j, x and y, however you guys want to break it up. We'll break it up into x and y. So if I were to do the gradient of f, and I want it to be the x1, or just the partial in respect to f, whatever you want to call it, what is that going to be equal to, you think?
48 x minus 2y.
Yep. Okay, cool. So that's that one. What is our gradient of y going to be?
6 minus 2x minus 18y.
Looks good to me. All right, cool. So there's that. Now let's do our gradients with g. So what do you think that is going to be? So something before we go with our g equation, we have our g equation here, but I think we can simplify that quite a bit. So with our g equation, right, all of these terms are divisible by 4, and all that we'll do is just scale. So we're going to simplify that g equation by dividing everything by 4. So our new g equation is going to look like this. It's going to be 5x plus y equals, I think that's 54. I believe that's what it should be. Yep. Cool. So there's our new g equation. So now what is our gradient of g going to be in respect to x? Going to be 5, right? Cool. Our gradient of g in respect to y? Going to equal 1. All right, cool. So now we're going to set up our equations, right? So we have our gradient of f is equal to lambda times the gradient of g. So we are going to match our x terms together and our y terms together, right? So if we were to do that, what is this going to look like? You guys tell me what the equations are going to look like.
X, that should be 48 minus 2x minus 2y is equal to just 5 lambda.
Correct. That is the ugliest looking lambda I've ever seen, but whatever. All right, and then what about our y1? All right, cool. And then, so what's the problem with this right here? What's our problem?
Constraint function.
We don't have our constraint function, right? We have three variables, two equations. That's not going to work. So we're going to add our constraint function, right? So it's going to be, I'm going to subtract this 54 over to the other side and set this equal to 0. So it's going to be, and I'm going to keep everything in line. So it's going to be negative 54 here, plus 5x plus y. So there we are. Any questions up to that point? Or are we good? Everybody see where we get the three equations from, everything like that? We all good? Cool. All right, now it's just solving a system of system of equations. We love it. So we can go through that. What do you guys want to do first? What do you guys think would be the best thing to do?
Could we divide our partial of the x function, the 48 one, by 5, and we just set them equal to each other?
We could, but I think in that case, we're going to be dealing with a lot of fractions. And I think that's going to be ugly. So instead of dividing by 5, what do you think we could do instead? Because we want to get rid of lambda. We don't care what lambda is. We only want to know what our x and y are, because that's what we're worried about with our profit. We could do that too, but I think the easiest thing here, if we want to get rid of lambda, is just to multiply this second equation by 5.
Oh, yeah, because then it scales it.
Mm-hmm. So if I were to multiply this by 5, we're going to get, I'm just going to rewrite the equations here. So it's going to be 48 minus 2x minus 2y equals 5 lambda. And then if I were to multiply 96 times 5, I'm pretty sure that gives me 432. Let me double check that. No, it gives me 480. That's what it is. So it's going to be 480 minus 10x minus 90y equals 5 lambda. So, yes. So, the way I like to do systems of equations is how I've always done it, is I set them up exactly like this, and I just put a little subtraction symbol right there. Because then you can just subtract straight down. So, you have 5 lambda minus 5 lambda, that's 0. Negative 2y minus a negative 90y, that's going to give you positive 88y, right? A negative 2x plus 10x, basically, so it's going to give you 8x. Then a 48 minus a negative 400 minus 480 is going to give you a negative 432. So, boom. Now we got rid of our lambdas. We don't care about lambdas. And now we have two equations with just x's and y's where we can solve. So let's do that. So now we have to set up a new system of equations. So we're going to have, I'm just going to go ahead and rewrite these the way that I like. I'm going to take both of these. I'm going to move these over here. So we're going to have 5x plus y minus 54 equals 0. And we're going to have 8x plus 88y minus 432 also equals 0. Cool. Now we just have to solve for one of our variables. Same thing. System of equations. We only have two equations this time. What do you guys want to do? What do you guys think will be the easiest way to solve this? We can do that. All right, so if we divide the second equation by 8, right? Or take that divided by 8, right? Then we're going to get just the second equation here. We're going to get x plus 11y minus what's 4032 divided by 8. Let's see here. I think that's going to be something like 54. Yep. Oh, look at that. That's nice and easy. All right, cool. So we have that. But if we were to, add or subtract those equations right now, we want to get rid of our constant. We don't want to do that. We want to get rid of one of our variables. So what do you guys want to do now? What y'all think?
Solve for just one over there? Is that the best way?
We could do, in terms of the other one, I think we could do that. But I think, again, the easiest way to do it is just going to do the subtraction method. That's just the way I've always done it. But if you guys want to do it that way, we can. I think this way is going to be easier personally. But again, it's whatever floats your boat. So we're going to just multiply this equation by 5 now. So we're going to divide by 8, then we're going to multiply it by 5. So now we're going to have 5x plus 55y minus whatever 54 times 5 is, 270. That still equals 0. So now we have this equation. We have this equation. So we're going to have 5x plus y minus 54 equals 0. And we're going to have 5x plus 55y minus 270 equals 0 still. And now we can just subtract these two terms, right? Get rid of our x's. Now we only have y's. So now it's going to have a negative 54y plus whatever that is, which is going to be 270 minus 54, which is going to be 216. Set that equal to 0, right? Take our y, we solve for our y, and that should give us 4. Everybody see where we got that? Any questions at all? Or you guys see that? We good? All right, cool. So now that y is equal to 4, we can just plug it back into one of our original equations. So let's just plug it back in to our g equation up here. So now we know what y equals 4. So let's plug that back in. So now we're going to have 5x plus 4 equals 54. 5x equals 50. X equals 10. And that is going to be our optimization. We're going to have to solve 10. Now, granted, these golf balls are in the tens are in the thousands, so it's going to be 10,000 golf balls for 4 hours of advertising. It's going to be our optimal scenario there. Any questions in regards to that problem with Lagrange multipliers?
Find one variable, pick any of the other functions.
I wouldn't say you could pick any of them because you don't know what lambda is, right? So if we plugged the 4y back into like one of our top 2 equations here, whatever. Yeah, you wouldn't know what lambda is. So it wouldn't be the easiest way to do it. I would just say once you find one of the variables, plug it into an equation that there's only one other variable and just solve it that way. Like that would be the easiest way to do it.
Like plugging into a constraint would be a good
Yeah.
option.
Yeah, most of the time, yeah. That'd be the best way to go. That way you make sure that you don't just get a like 0 equals 0 situation either. That make sense? Cool. All right. So that is our Lagrange multipliers. That's just showing exactly what we did. We got the same answers. That's good. Cool. Now for double integrals. Yeah, you're back.
Sweet. Okay. This is talking about some properties of our double integrals. A lot of them are very similar to our regular integrals, right? We can separate out constants. We can sum up a couple of them and then separate them into 2 different integrals, all that kind of jazz. And then a good one to know is that we can switch our bounds, right? We can switch from dy to dx as long as we account for that in our bounds and it's continuous, right? Okay. Do you guys want to go through an example of our double integrals? Or do you feel pretty solid? You feel pretty good? Okay. Sure.
So volume inside of the 3D shape. What is that? It doesn't sound. No, I believe it's area.
More, how do I say this?
You mean the triple integral define the volume.
Yes, if you're
Define
more mass, yes. So kind of a way of thinking about it is how I like to think about it is if our triple integral is equal to the total mass of the shape, then any function we have in here is going to be like the density of that shape. And if it's 1, then it's the volume of the shape. But if we know, we can also use a double integral to find the volume of our shape if it's using a function. So basically all we're doing is we're taking this one and then we're plugging it in here.
And then the double integral on the area.
Yes. Yes, exactly. So that's kind of how it translates to volume. So kind of depends, but a lot of times we're just plugging that back into there. Sweet. And then do you guys feel comfortable about like switching bounds if you have to? If it's like a function, you know what I mean?
Yeah.
Yeah.
Just switching like, oh, x is 0 to 1, y is 0 to 2. You just switch those around and you integrate y first instead
Yeah.
of x. Right?
And then if one of your bounds is like y equals x squared plus 2, for example, then how would you?
Subtract the 2 and then square root the y minus
So you
2
solve,
function.
yeah, you solve for x, and then you do have to check whether it's still the upper bound or the lower bound. Sometimes they'll switch. So you know. But yeah, sounds like you guys got a pretty good handle on it. Woo, sweet. Okay. And how do you triple integrals then? Do you want to talk about it, or we're just? I mean, it's the same thing. It's saying you can switch the bounds. Same thing. It's just saying you can switch the bounds around as long as it's continuous. Where, yeah, yeah, yep, yeah. And then separable is just if they're individual functions, meaning it's not separable if you have like a cosine of x, y. Now, yeah, then you can separate them out. Yeah, that's all that one is saying. Yep, totally. Okay. Do you guys want to talk about transformations? Okay. Howard's turn. That was a fast one for me.
It's gonna take a little bit. And actually, I'm pretty sure this is the last thing we have in the slides too. So after this, we can just you guys can ask all the questions you want. All right. Transformations. Cool. So transformations are basically a way of changing from one coordinate system to another. So that would be like in double integrals. Like for example, a basic one would be like going from the double integral of like some, x and y function to some double integral of r and theta would be like probably the most basic version that you guys will encounter most of the time. So that's basically all it is transformations. So now we can go into kind of what they are and a little bit more in depth into them. So with transformations, you have the Jacobian. I know it looks really scary. It's very scary, right? But all it is a bunch of partials and a determinant. That's really all it is, right? Looks uglier than it is, right? So the reason that we have to use the Jacobian is because when we transform from one like coordinate system to another, you have to take into account the changes in the coordinate system. So if you guys want, I can go a little bit more in depth in that, or you guys can or we can just move on. What do you guys think?
Triple like that bottom one.
You want to do the triple one? Let's see if it goes into this or not. It does not. All right, cool. So if you wanted to find the Jacobian of that 3 by 3, right? And you guys will learn this in Lindith if you guys take this as well. But all you would do is just take the determinant of a 3 by 3 matrix. So how you would do that is as follows. Huh? Basically, yeah. So it's just, IJK, just like normal, right? So you'd take this one, multiply it by the cross product of these two, right? And then you would take this one, multiply it by the determinant of this 4 by 4. Yeah. So if I were to write this all out, because that looks really ugly, right? I'll write out the formula for it right now. So first, you take the top left term right here. You would take the partial of x in respect to u, and that would be multiplied by the determinant of this 4 by 4, which would be the partial of y in respect to v times the partial of z in respect to w minus the partial of y in respect to w times the partial of z in respect to v. See that?
Yeah, that makes a lot of sense because I was curious about how that works.
Yeah, and then it's the same thing, right? So then it's minus, right? Because it's IJK, right? Minus, and then we would do the next one. So then it would be
Times, and then that would be partial of y in respect to u times partial of z in respect to w
yep,
minus partial W in respect, the partial of Y in respect to W.
Mhm.
Times the partial of Z in respect to U.
Exactly. And then so on and so forth, and then you would add the last term. But yeah, that is how you take the determinant of a that's called the determinant of a 3x3 matrix. Yeah. So it's kind of fun. And then if you wanted to do a 4x4, it's the same thing. Just, you got to do it, what, 16 more times? Is that right? 12 more times? Something like that. Yeah, it's you will never have to do that. You might have to do it once on a practice exam for Hevlin or something, but I feel like I never did that by hand. Yeah, so that's how you do that. But hopefully you never really have to do it that much. That's why we have calculators now. But you should know how to do it by hand. It's very important. It is really good to know. And matrices are super important. So now we can go over next step. So changing the new coordinate system to change variables. So example, find the Jacobian for the transformation to polar coordinates. This one's just a basic 2x2, right? So if we had some sort of function, right? We had some sort of function x. If we had like the double integral of, let's just f of xy, right? Something like that. If we wanted to transform it into polar coordinates, it'll have to be the double integral of a new function in terms of r and theta, but we have to multiply by whatever the Jacobian of that transformation is, which I don't know if you guys know what it is already. It is r, right? Yeah, the Jacobian is just equal to r, but we're going to derive that. And I'm going to show you guys where that comes from. So let's derive it. Sound good?
Yeah.
All right, cool. Let's do it. So let's start off with what we know. What is x in polar coordinates?
Cosine, R cosine theta.
R cosine theta. And what's y? Cool. So going back to what we did previously, right? Looking at the Jacobian. If we want to define what the Jacobian of our transformation is going to be, what do we need to do?
Partial theta.
Yes, we do. So if we did, so let's just write them out. I'm just going to write them out left side, right side, up here. So let's do partial of, not f, there's no f here, Howard. Partial of x in respect to r. What's that going to be?
Cosine theta.
Cosine theta. Cool. Partial of x in respect to theta.
All negative R sine theta.
Right? Cool. All right. Partial of y in respect to r. Sine theta. Partial of y in respect to theta. R cosine theta. Cool. Sounds good. So now let's set up our Jacobian matrix, right? What's that going to be? What we got?
Cosine theta,
Okay.
negative R sine theta. And then sine theta, R cosine theta.
Looks good to me. All right. So if we were to take the Jacobian of that, what are we going to do?
So cosine times sine theta, we get us R cosine squared theta
Mm-hmm. Minus.
minus a negative R sine squared theta.
Cool. So we can get rid of these minus symbols, right? We can just
Yeah.
make it plus. Cool. So now we have r cosine squared theta.
R sine squared theta.
Mm-hmm. What can we do?
Pull out the R for each term. And cosine squared and sine squared simplify to 1. It's a trick that we
Yep.
just saw.
That is a weird V looking R. R. Cool. So boom. Now you know how to derive Jacobians. They're fun. So now if I were to give you the spherical coordinate transformations, you guys could do it, right? I won't make you do that. I'm not going to make you do that today. But you guys could. You guys could. You ever forget, you ever forget what your Jacobian is.
Brute force done in my brain.
That's fair enough. But hey, like I said, you ever forget, you know how to find it, right? So yeah, it's just going over what we did. You don't want me to do that? That's-
Take this off exams.
Well, we're doing it today. No, I'm kidding. All right. So now we're just going to do an example problem with transformation. So that one was just finding the Jacobian. Now we're going to do a whole example problem. Okay. And this will be the last thing we do today. So we're going to evaluate the triple integral of this function right here, where E is some shape that is bounded by a solid cone, where Z is equal to this and the plane 2. So what's this telling us first off? What you guys think? Telling us lots of things. Cool. I like it. Z is equal to R. Okay. What else? What else we got? I want to double check something. I don't want to do that yet.
Yeah,
It's cone, right? Okay. Okay. So we're gonna do we know we're gonna do a transformation, right? Into either polar or spherical. Which one?
spherical.
Spherical.
Right. We're doing triple integral.
What you could do, obviously,
That is fact, yeah.
So here's a way you guys can think about it, right? To make it more clear. Let's draw the cone. Let's draw it in 3 dimensions, because why not, right? So I'm going to do my best to draw in 3 dimensions. Humor me. So we're going to have our axes here, right? We're going to call this our z-axis. This can be call this our x-axis or y-axis or whatever. Maybe that's not exactly right. I don't exactly remember. But the important thing is just to draw the shape. So we're going to have a cone where it's going to be bounded by the plane z equals 2, right? And it's going to look, it's going to start at the origin, and it's going to look something like that, where it starts off at z equals 2. That's not a great drawing. I'm trying to think how I can better draw that. Let's see. So we have our cone here, and this is our z-axis, right? So, right, this is a circle, basically, going all the way up. So if we were to look down on this in the xy plane, right, all it would look like, so if this is our x, this is our y, it would just look like this, right? But it's not like turning or anything like that in the z direction. It's just going straight up. So the best way to do this problem is going to be what? What do you guys think we could do? Because we know we're going to have to at least put it into circular coordinates, right? Into r and theta. But do we need phi here? Or can we just keep it in z? Keep it in z, right? Because r is going to change as it increases, right? But z is just going to remain the same value. So we're going to have it, so our axes that we're going to transform it into are going to be z, r, and theta. That's going to be our transformation. So
when would the case happen where you would use spherical over like cylindrical?
that is where you probably will have a sphere of some sort.
When it gives you a sphere.
Yeah, so like if you, the biggest help with that is just going to be thinking about what shape it's asking you about. So with a cone, it's not, we're just having a circle increase in radius as it goes up. The z value isn't rotating, it's not doing anything special, it's just increasing, you know, as just with integers, just nice and up, right? But let's say we had a freaking cylinder. Say we had a cylinder, right? And it was along an axis. We know we're going to have to put it into, you know, circular again, because we're going to have some sort of radius, we're going to have some 2 pi to make us a circle. But again, it's just increasing one direction. It's not rotating that other direction, it's just going straight. Exactly. So our r wouldn't even change either. Right? So that's where the best way to do that is just to be thinking about the problem and what the shape looks like. That would be the best. That'd be my best advice. Yeah.
If it's only revolved around one axis, then I would use cylindrical or polar coordinates. If it's revolved around multiple axes, that's when you're going to if it's revolving around 2 of them at the same time. Or in other words, if you could like look at the, I don't know how to say this. I can never remember which plane it is, but if you could look at a plane and it's a normal shape that's not a circle, then use cylindrical coordinates. If you're looking at it like in 2 dimensions on one plane and it's a circle, probably gonna need to use spherical.
Yeah, I really like the revolving around one axis thing. That makes a lot of sense too. Does that make sense? A little bit more? And the best way to do it, I think, would just be to get practice with it as well. But just, yeah, the best way to think about it is, does it rotate around this axis? If it doesn't, you're probably not going to need to use spherical. Does it rotate around one axis? Yes. Does it rotate around two? No. Okay, that means I'm just going to use symmetrical. Yep. So we are going to transform this into r, theta, and we're going to keep z the same. Cool. So the most important part of this is going to be figuring out our bounds. So I think this will tell us what our bounds are. Does it? It does. So we're going to get to here. So we know that z is equal to r, right? Right here. Now, I don't remember, did I change this? I did. Okay, cool. This slide was messed up when I fixed it earlier. All right, cool. So we're going to set up our bounds. So what do we know about our bounds? What do we know about our theta? It's going to go from 0 to 2 pi, right? So now here's where it might get a little confusing, right? So we're going to have our integral, right? And the last one's going to be 0 to 2 pi, and that's d theta. But the next two are going to be either in terms of r or in terms of z. And that's where we have to make a determination of which one we're going to do. So z is equal to r, which means one of our bounds is going to have either a z or an r in it. We don't know which one it's going to be. We can make that decision for ourselves, and you can even do it both ways. It's whatever way makes sense to you. So here's the way that I think about it. It's what makes most sense to me. If you think about it a different way that makes more sense to you, do it that way. But to me, I'm thinking, okay, we know that z ends at 2. We know that that's our upper bound for z. We know that, right? So I'm thinking, okay, I'm just going to put my upper bound as 2 there. It does not go past that plane, z equals 2. We know it ends there. But then what's it going to start at? Well, it's just going to start at 0 because it's a cone. And it's not, the cone isn't like moved anywhere. It's just starting at the origin going up, right? That's how you can think about it. So it's going to start at 0. Easy. Okay, well, what about r? Well, r is also going to start at 0. But what's it going to? It is, but does it automatically to the entire, is it to the entire way up? Is my question. No. So what is it as it goes up? BZ, right? That's what that part right here is telling us. As z goes up, our radius is also going to increase at the same rate. That's what makes the cone shape. So like when z is 1, our radius is 1. When z is 2, our radius is 2, so on and so forth, right? And that's where you get that cone shape, is from that equation right there. So that's the best way I like to think about it. And actually, this isn't going to be r, this is going to be z. Right there. Yeah. So our r increases as z increases. It's not just 0 to 2, because if it was 0 to 2, then we'd have a cylinder. But it's a cone, so it's increasing as z increases. Z, we know, goes from 0 to 2, and then we know theta is just 0 to 2 pi. That's automatic, right? All right, cool. So now we can just set up our equation. So we kept z, and we're not in spherical. We're in circular. We're not in spherical, we're in circular. So we can think about it. So we have z here still, because that's our function. We didn't change z. It's still just z. Yep. So then if we transformed it, our dv, from an x and y into r and theta, what do we need? Which is r. Perfect. And then our derivatives here are r, dz, d theta. What order are they in?
R, Z, theta.
Yep. Are you guys good on that so far? Cool. All right, so now it's just evaluating the integral. We've done the hard part. Now it's just evaluating the integral. So how do you guys want to evaluate it? Or do you guys want to do it? You guys want me to walk through it? I mean, it's a triple integral. I think you guys know how to do it. So I'll just start walking through it. And if you guys have any questions, just stop me. So we'll look at our first part here. I'm just going to look at this part, just the dr. So we're going to have the integral from 0 to z of z times r dr, which is going to be z times r squared over 2, evaluated from 0 to z, which is going to equal z cubed over 2. Cool. So now I can go to the next one. So now we're going to have the integral from 0 to 2 of z cubed over 2 dz. That is going to turn into z to the 4th over 8, evaluated from 0 to 2, which is just going to equal 16 over 8, which is going to equal 2. So we knocked out 2 of our integrals. Now we just have 1 more. So the integral 0 to 2 pi of 2 d theta, which is just going to equal 2 theta by way from 0 to 2 pi, which is going to equal 4 pi. And there you go. That is all it is. Any questions on that? Cool. So one thing I'm going to point out real quick is the actual integral itself. So, and Izzy was actually there when I asked my coworker about this question too. So normally, when you're just evaluating the volume of a function, you are only going to have the triple integral of 1 dv because your bounds take care of finding the area for you. That's why we have like 0 to z in the bounds here, 0 to 2. That's what our bounds take care of, is finding the actual volume. That's this z right here. It could be anything. It could be evaluating something different. So like the easiest way I could think about it is, imagine this z was density. Then once we evaluate it, we would take our density times our volume. That gives us our mass. So instead of just evaluating the volume, we evaluate our mass. So if it's just a 1 dV, you're evaluating your volume. If there's a value in there, odds are you're evaluating something else, depending on what z is. But you guys could do it either way. You guys know how to do it now? So if it was just 1 dV, then instead of having the z times r, it would just be r, dr dz d theta. That make sense? Cool. Any questions on that? Yes, feel pretty good? Cool. And I think that is all I have for the rest of it. So do you guys have any questions from anything you guys might want to go over again or anything like that? Or just maybe we could come up with some more examples, I don't know. Or if you guys are all good, we can call it early, whatever you guys want to do. You guys have us till 7, so it's whatever y'all want. Yes, there is a second Calc 3 review tomorrow night. And that is over like all the chapter 6 stuff, as far as I know. Also 5 and 7? Okay, cool. Oh yeah, it's also 5 to 7 tomorrow. Yeah. And I don't know if it's in the same room or not. It is? Cool. But yeah, anything you guys want to go over? Anything else? Anything from the from chapter 4 and 5 that you guys want to go over? Chapter 6 is for tomorrow. But. All right, cool. Sounds good. I think that's what everybody's going to be coming in for.